Welcome to our deep dive. We're tackling the Algorithm Design Manual today, the one by Steven Skiena. Um, it's kind of classic, right?
Yeah, and for good reason. Like,
Sure.
it doesn't just throw theory at you. It actually helps you, like, get practical, build
Little-
algorithms.
It's what I like too. It's about making stuff. And then there's those war stories, those real-world examples. Have you ever seen algorithms used like that?
Oh, they're what makes it click.
Hmm.
It's one thing to talk about, like, sorting numbers, but then Skeen's like, boom, here's how it optimized delivery routes.
Or even, remember that one? Reconstructing text messages, but just from the phone keypad. Wild, right?
Exactly. And the best part, he's got this whole online code repository, so you can actually try the stuff out.
Hands-on, that's what I'm all about. So these war stories,
Hmm.
why do you think he leans on them so much?
It's bridging the gap, right? You got the theory, all fancy, but then, bam, a real problem solved with the algorithm. They show the impact. Algorithm actually doing stuff.
Like, it's not just a textbook thing. It's out there in the world.
Makes sense. Okay, but before we get to the, specific algorithms, how do we even measure how good they are?
Efficiency, right. That's key. So the book starts with this thing, the RAM model. It's simplifying how computers work. Each step, like adding or comparing, takes time.
So it's like a level playing field. No matter what computer you're on, it's about the algorithm itself.
Yeah, yeah. But then the problem is, like, time depends on how much stuff you're working with, the input size, right? That's where big O notation swoops in.
Ah, big O. It's about how the time scales, not the exact number of steps.
Exactly. Like, imagine two sorting algorithms. One's O(n) log n time, the other's O(n). Smallest, maybe no biggie. Huge list. O(n) takes forever.
Well, that's like, I don't know, finding a grain of sand on the beach versus counting every grain on the planet.
You got it. So choosing the wrong algorithm, especially with big data, it's disastrous.
So big O matters, but how do we even make these efficient algorithms in the first place?
No.
One word. Data structures. How we organize the information. Like, imagine a toolbox. You got to find the right tool fast, right?
I get the analogy. So the book's got contiguous and linked. What's that all about?
Contiguous, think arrays. It's like things lined up perfectly in memory. Accessing any of them, super quick, but inserting and deleting, gotta shift everything.
Okay, so linked, that's the opposite.
Yeah, they're like chains, pointers, connecting them wherever they are in memory. Inserting's a breeze, but finding stuff. Gotta follow the chain, slower.
So trade-offs everywhere. Now there's this thing, hash tables. Everyone loves those for finding data fast.
They're like the speed demons. It's about this hash function, a special labeling system, right? Map stuff to places in an array, find something, calculate its label, bam, you're there.
Why so much faster than, like, just searching a list or something?
Think super organized warehouse. Each item's got a unique label, and they know exactly where it goes. But then, uh-oh, what if two things get the same label?
That's got to cause problems.
Collisions, yeah. But there's tricks. Chaining, it's like a backup list at each spot. Or open addressing, you just scoot over to the next free space.
Clever, I bet they use this everywhere, right? Not just in theory.
Oh yeah, everywhere. Spell checkers, databases, anytime you need to find something quickly. Now let's shift gears a bit. Sorting. Ever think about that?
Seems pretty basic, just putting things in order.
But it's, like, fundamental. So many other algorithms rely on sorted data. Want to search fast, sorted list, binary search, boom. Or find duplicates, medians. It's like organizing your life.
Okay, I see. Now, the book's got all these sorts: insertion, selection, heap sort, quick sort. Which ones matter?
We don't need the nitty-gritty details, honestly. It's the big picture. Simple ones like insertion sort, slow for big data, quick sort, merge sort, they're the heavy hitters.
Could you, like, give me an analogy so I
Oh.
can picture it?
Sure, think cards. Insertion sort, you're picking a card, putting it where it goes in your hand. Selection sort, you're finding the smallest card, then the next smallest, and so on. Merge sort, you're dividing the deck, sorting the halves, then merging them together.
I like that. Different strategies for different situations. But there's got to be a limit, right? How fast can we even sort stuff?
Oh yeah, the book talks about that, the sorting lower bound, omega of n log n. No matter how clever we get, comparison-based sorting can't be faster than that.
That's a hard limit.
Yeah.
Cool. Okay, shifting gears again, let's talk graphs.
Graphs, they're all about relationships, right?
Uh-huh.
Roads, social networks, even the flow of a program. Anywhere you've got connections, you got a graph.
And there's different ways to represent those in a computer, right? What were those?
You get adjacency matrices. It's like a table. Each cell's a yes or no for a connection. Simple, but can be huge and mostly empty if there's not many connections.
So for those sparse graphs, what's the alternative?
Adjacency lists.
Yeah.
It's just a list of who's connected to who. Saves space, but Maybe a bit slower for some tasks.
Trade-offs, trade-offs. Now, once you got your graph, you got to explore it, right?
Right.
DFS and BFS, what are those all about?
They're how we explore systematically.
Mhm.
DFS, it's like going down a rabbit hole as deep as possible, then backing up. BFS, it's more like expanding outward, layer by layer.
I see. Different ways to walk through the graph, and they're like the basis for other algorithms
Oh,
too.
absolutely. Finding the shortest path, seeing if everything's connected, detecting loops. It all starts with these traversals. Like, remember that story about reconstructing text that used this stuff?
Yeah, it's crazy how those basic traversals can be so powerful. And the book goes even deeper, right? Spanning trees, shortest paths. What are those all about?
Spanning trees, imagine connecting a bunch of cities with cables, but as cheaply as possible. That's it. Shortest paths, like Google Maps, finding the best route. Network flow, it's like maximizing water flow through
That's
pipes.
super practical.
Hmm.
Okay, now on to something that always messes with my head. Intractable problems heuristics. And this P versus NP thing, right?
Oh, yeah, the big one. It's about, like, can we solve any problem quickly if we can check the solution quickly? Some things are easy to check, but finding the solution might take forever.
So are some problems just, like, impossible to solve efficiently?
That's the question, basically. P problems, we can solve them quickly. Polynomial time. NP problems, we can check them quickly. But who knows if we can solve them quickly?
And NP complete, those are the big baddies.
Yeah, the hardest of the hard. If we cracked any of them, P would equal NP, would be huge. But until then, we use heuristics.
So those are like educated guesses, right? Not perfect, but good enough.
Exactly. Backtracking's one. It's like trying all the paths in a maze. Then you got simulated annealing. It's like shaking a snow globe and seeing where the flakes settle. Randomness can help.
Fascinating. So much to think about. We've covered tons already. Those war stories to make it real. Big O, data structures, sorting, graphs,
Yeah,
even this P versus NP mystery.
that's just part one. Next time, we're diving into dynamic programming. Buckle up.
Welcome back. We're continuing our deep dive into the Algorithm Design Manual. We've covered some basics. Now it's time for something a little trickier, dynamic programming.
Okay, gotta admit, that one always makes me nervous. Like, is it as hard as it sounds?
It's got a reputation, yeah. But honestly, the idea is simple. It's all about breaking a problem down into these smaller pieces, sub-problems, they overlap. And the key is you save the answers so you don't redo the work a million times.
Okay, that kind of makes sense. But, like, can you give me a real-world thing so I can picture it?
All right, imagine you're trying to find the best route from home to work. Traffic, roadblocks, tolls, the whole mess. Now, you could try every single possible way to go, but yikes, right?
Yeah, my brain would melt. There's got to be a shortcut.
That's where dynamic programming comes in. Instead of this giant problem, we break it up. Like first, figure out the best way from every intersection to your work, then from your house to those intersections, using the stuff we already figured out. So it's like a puzzle, but you build it from smaller pieces first.
You got it. And by saving those solutions, we're not wasting time recalculating every time.
Like a map with pre-calculated bits, so you don't got to start from scratch. Now, the book uses Fibonacci numbers as an example. Those always seem kind of pointless to me, like just a math game.
They do seem that way, but they show up in nature too, you know?
Yeah.
Petal arrangements, branches on a tree. And the cool part is, if you try calculating them without this dynamic programming, you're doing way too much work.
Too much work. How so?
Let's say fifth Fibonacci number. To get that, you need the fourth and the third, right?
Yeah.
But for the fourth, you need the third again, and so on. It's a mess of repetition.
Like taking the scenic route when you could have just gone straight there.
Dynamic programming's the straight route. You build a table, store the values, need it, boom, look it up. No recalculating.
So no wasted effort. Makes sense. Now, the book's got other examples too, right? Like edit distance and that knapsack problem.
Yeah.
I mean, what are those about?
Okay, edit distance is how similar two strings are, like how many changes to turn one word into another, typos, think of it that way.
Spell checkers, stuff like that.
Exactly.
Yeah.
Or comparing DNA sequences, even finding plagiarism, and dynamic programming makes it fast. Then there's the knapsack, classic one. You got a bag, limited space, and items with values and weights. Got to pick the best stuff to maximize value, but stay under the weight limit.
Like packing for a trip. My suitcase is always too small.
Perfect example. And it's not just packing, it's in resource allocation, finance, tons of places. Dynamic programming helps us find the best solution without trying every single combination.
So it's a powerful tool when you can use it. Right. Okay, let's switch gears again. What about these numerical problems? They sound, I don't know, more straightforward, just math. right?
Yeah, numerical problems, they're all about numbers and calculations. Simple stuff, but also things like solving equations, finding roots, matrix operations. We take the math, make it algorithmic.
Gotcha. So, like the book talks about Gaussian elimination. I vaguely remember that, didn't really get it at the time.
It's for systems of equations. Basically, you manipulate them, adding, scaling, until you isolate the variables and get the solution. Like, think Sudoku, how you strategically fill in the
Oh,
numbers.
that's a way better way to picture it. And then finding roots of polynomials. That sounds tough.
Can be. For higher degree polynomials, no magic formula. But there's methods, like Newton's method, they get you close, iteratively, like a guessing game, higher or lower, till you hit the target.
Ah, I get that. And these methods, they're used in tons of fields, right?
Oh yeah, physics, engineering, even computer graphics, you can't escape them. Now, matrix multiplication, you'd think that's simple, right? Just multiplying.
Yeah, what's tricky about that?
Well, the usual way, it gets slow for big matrices, 0 and 3 time, that's a lot. But there's faster tricks like Strasson's algorithm, even simple stuff can be optimized.
Cool. So even with matrices, gotta think about efficiency. The book also mentions numerical stability. What's that all about?
It's about how sensitive an algorithm is to rounding errors. Computers use these floating point numbers, they're not perfect. Some algorithms, they amplify those tiny errors, you end up with garbage results.
This is like, I don't know, a rumor spreading, and each person makes it a little worse.
Exactly. Unstable algorithms, the gossipy friend, twisting the story. Stable one's the reliable one, sticking to the facts.
Reliability is good.
Yeah.
So how do we avoid those unstable ones?
It's a whole thing, but basically, choosing stable algorithms, being careful about subtracting numbers that are really close, ordering operations right, gotta minimize those errors.
It's like accuracy matters just as much as speed, especially in the real world.
Absolutely. Slow and steady wins the race, sometimes.
Yeah.
Okay, so we've done dynamic programming, delved into numerical stuff, ready for the next challenge.
Hit me with it. What's next on this algorithm adventure?
Next up, we're entering the world of combinatorial problems. Get ready to count, generate, and search for all sorts of cool stuff. Permutations, subsets, trees, graphs. The possibilities are endless.
And we're back for the final part of our algorithm design manual deep dive. We've done the basics, tackled dynamic programming, even wrestled with numbers. Now it's time for, what was it? Combinatorial problems.
You got it. This is all about like arrangements, combinations, selections, how many ways to do something. Think shuffling cards, picking a team, that kind of thing.
Okay, I kind of get it, but does this stuff actually matter in the real world? It seems like, I don't know, very mathy.
Oh, it's more common than you think. Imagine like scheduling a factory. Which task goes on which machine, when, with which worker. That's all about finding the best order, a permutation.
Okay, I see. Or like routing data through a network. Gotta find the best path, considering all the options.
Exactly. And that's where algorithms for generating and analyzing these combinatorial objects come in.
So let's start simple. Permutations, I remember that word. Is there a standard way to list them out?
The most common way is lexicographic order. Think alphabetical, but for any kind of sequence. Often, though, the order doesn't really matter as long as you get each permutation once and only once. And sometimes a different order might even make the algorithm faster.
So it's like shuffling. The order of the shuffle doesn't matter, just that every arrangement is possible.
You got it. And Skeena's got a bunch of algorithms for this, both lexicographic and not.
Okay, what about subsets? Like all the possible groups you can make from a set. That seems like it could explode pretty quickly.
Oh, it definitely can. But there's techniques like backtracking that help us explore systematically. And then there's these things called gray codes. They generate subsets where each one's only a tiny bit different from the one before it.
Gray codes. Never heard of those. What's the deal with them?
Think of it like a row of light switches. You flip one at a time, that's the idea. Each subset is like a different pattern of switches. They're used in error correction, circuit design, even puzzles.
Interesting. Okay, another one I remember vaguely, partitions. Dividing stuff up into groups. What kind of problems involve that?
Well, one classic one is just counting how many ways to partition a set, like dividing students into project teams. How many ways can you do it?
And I'm guessing there are algorithms to actually make those partitions, not just count them.
Of course. Backtracking comes in handy here, too.
Now, the book gets into generating stuff for graphs, too. Trees, graphs with specific properties. That sounds complicated.
It can be. But think of it like designing a network. You want to see all the possible ways to connect things to find the most reliable one. Or maybe you're analyzing a social network, looking for patterns. Algorithms can help us generate those structures.
Wow, so many applications. It's amazing to see how this combinatorial stuff pops up everywhere. We've covered so much in this deep dive. It's hard to believe it's already the end.
Yeah, it's been a whirlwind tour. We've barely scratched the surface, but hopefully it's given you a sense of what algorithms can do and maybe spark some curiosity to explore further.
Absolutely. The Algorithm Design Manual, it's a treasure trove. Whether you're like a hardcore programmer or just curious about how this stuff works, I can't recommend it enough. Thanks for joining us on this deep dive